Alright, so that was just for first ionization energies. Now let's talk a little bit about second ionization energies, because that's going to become kind of an interesting thing to look at. So if you take your first ionization energy, that's to take off one electron. Your second ionization energy is to take off another one, and therefore your second. Okay. Third ionization energy would be to take off number 3, fourth 4, fifth 5, etc., etc. Okay, so if you look at these values, okay, one of the things you'll note is that here we have an element in the third row of the table. So we're just given that it's the third row in the periodic table. Has so somewhere in between here, sodium, magnesium, all the way out to argon. It has the following ionization energies: 578 kilojoules per mole. 1,820 kilojoules per mole is the second ionization energy. 2,740 kilojoules per mole is the third, and 11,600 is the fourth. One of the things you'll note is that every single ionization energy and a successive ionization energies here increases. That's because once you take one away, right, you've taken away some of the shielding, some of the repulsion there, and you have not taken away any protons, so there's a higher effective nuclear charge for the next one in. Okay, what you're looking for in this case is a big jump. So we go 578, 1820, 2740, 11,600. So that 11,600 represents a pretty large jump in ionization energy. And what that means is you're taking that fourth electron, in this case, off something that is substantially stronger hold on it than it did the previous three. Okay, so if we look at our row right here that we're looking at, what we're really looking for is something where the first three come off reasonably easy, and then it's very, very hard to take off the fourth. So if you were to start over here at argon, okay, let's say take off one, I would go to the same as chlorine, so I would be at 3p5, 3p4, 3p3 would be, this doesn't really seem to make a lot of sense why the third to fourth then would be a big jump. If we, however, start with aluminum, especially if we know we're taking them off relatively easily, going to be something forming a positive charge, removing the first one gives you 3s2, removing the second one gives you 3s1, removing the third gives you 3s0, or essentially the same as neon, but then that fourth one, we're now going to have to take it out of the 2p orbital. Right, so we're dealing with aluminum, which has 13 protons in it, and we're trying to get it to an electron configuration that is similar to fluorine. Okay, it's not going to want to remove the one from the 2p. Those things are held in very, very tightly, and that's why you see this drastic increase. So what you're looking at here is the element is most likely going to be aluminum, and the reason we know is because that third jump is the fourth jump, sorry, is so high, and that means that you're now taking out of an entirely new and very difficult shell.